Dear friends, welcome to Łódź, Poland for the 5th International Scientific Conference of Spatial Econometrics and Regional Economic Analysis. As you see, I am not here in body, but I am present here in full mind. First, I like to thank my dear friend Alicia for making this presentation possible. I am also very much thankful to the organizing committee for this wonderful conference, gathering. I would call it a clustering. I have had the privilege to attend this conference from the very first meeting, and I also attended some of the subsequent ones. And when I was here for the first time, I talked again in a broad sense of the spatial analysis from the beginning to the frontier of spatial econometrics. And when we talk about spatial analysis, we mostly concentrate on spatial dependence and sometimes spatial heterogeneity. So dependence is the key word. And what I would say, dependence is best understood in Poland. Okay, if you want to prove, here it is. Okay, see this guy? I'm sure all of you recognize him. He's the legendary Jerzy Neyman. If we go back 100 years, 1918, the number of statisticians was just one, not any fraction, more than one. Now in 2018, how many statisticians are there? Even in this room, the spatial econometricians, I am sure, will be close to 100. He was a lecturer here in the Department of Agriculture, giving lectures 25 hours per week and earning $6 per month. No, and even with all the inflation, $6 was not much that time. And in terms of his work, his bosses, Professors Sapinski and Basalik, told him, "Look, Mr. Neyman, we don't understand what you are doing." Because Neyman was really a mathematician and he was doing very sophisticated technical work. So they told him, "We don't understand what you do, and we can evaluate you. So the only way we will know you are good if you can go to England, work under Professor Carl Pearson, and publish a paper in journal Biometrica. Then we'll know you are okay. Otherwise, you don't come back." So they arranged a government scholarship of 25 pound per month. That's a fortune that time. And Neyman arrived University College London in September 1925. He met Carl Pearson, gave him a translation, English translation of his paper, and arranged to meet him after 1 month. In October 1925, they met. Neyman went to his office, and Pearson was a very efficient person. I mean, he was, of course, one of the founder, I would say, grandfather of statistics. Father would be the modern statistics would be R. Fisher. He read the paper, and he was happy with the paper, except for one line. So he told Neyman that, take out this line, where Neyman wrote that mean and variance are independent for just, in a very special case of one Pearson frequency curve, that's the normal distribution. But Pearson didn't agree, and Neyman, with his inadequate English, tried to convince him. And Pearson was, maybe this is the first time in his life somebody was arguing with him, and started to get angry. At one stage, then he told Neyman, "Look, Mr. Neyman, this must be true in Poland, but not here. Now you get out of my room." And Neyman was completely frustrated and thought that's the end of it. He cannot go back anymore to his old job. Luckily for him, Carl Pearson's son, the junior Pearson, Egon Pearson, who was basically Neyman's age, came to rescue him. And he went back to his father, telling that, Naaman has really made a big mistake, and he really wants to get the paper published. So eventually the paper was published in Biometrica, and that saved the day for Naaman. Anyway, so now going back to the real topic of my today's talk, for this fifth clustering, I'll attempt to broaden the scope of my talk that I gave, how many years back? That will be 8 years back. So now here is the new title: Spatial Analysis from the beginning of the civilization to its very end. No, I really don't want to scare you, but once you make a topic broad enough, that means you can put everything there, like clustering, Mars, massage parlor, end of civilization, all kinds of things. So I want to have this flexibility. Okay? So that's why, deliberately I have this, very broad title. Okay. Oh, now I am in a new outfit. In fact, I wanted to make this talk very simple and enjoyable, like the Bollywood movies. If you remember, in those movies, the outfits of hero and heroine, change many times, even in a single sequence of song and dance. But the highlight of this particular my outfit is, that it has a logo on my university, ANU, Australian National University, from where I got my PhD in 1983. Okay, and also I should say also, I will avoid using any questions but plenty of pictures. So sit back and relax. Okay, so we already mentioned clustering, and you can see its ubiquitous presence at many places. Like as I said, in this room too, there are clusters, there are subclusters. Possibly those who just returned from Vienna Sea are sitting together. That is a kind of time-space clustering. You also sat together at sea, now you are sat together at woods. Once in Russia, I walked to a corner flower shop and found that the shop automatically leads to a liquor shop, but with a different street address because it was a corner shop. And I also saw this kind of clustering of liquor and flower other places. Now look at all these photos. These are real photos. Okay, so take your time. Look at these photos. But you might ask, why they have put, these two kind of shops together. Here is the earthly region. Husband goes home with a bottle of liquor, wine, vodka, whatever, in his right hand. Of course, naturally, the wife gets annoyed. But before she, burst into, a storm, husband, reveals his left hand from his backside with a bunch of beautiful, fresh red roses. Problem solved. Okay. Anyway, so this is again a kind of simple life, where you see clustering. Now let us think a little bit bigger than this. As I said about the human civilization, and once you look at this slide, you see that it clusters around only in a few spots in the whole world. I mean, Homo sapiens have been in this world for thousands of years, but the civilization, progress came much later. Let us kind of briefly look at one spot. say, which I know a little bit more than other ones, this Indus Valley civilization. Okay, and the Stone Age was very long. Kind of, as we see, it was 63,000 years, at least in South Asia. Okay, and nothing much happened. But then the next age, what we call Chalcolithic age. This Chalcolithic is a very mouthful word. The Chakos in Greek means copper, and lithos means stone. And this is the age when copper came into the picture, but people are still using, of course, stones to make their, tools. And we will talk about these tools also. It's very important. And so then, after the 7,000 years of Chalcolithic age, then we had this, Indus Valley civilization. Okay, so then I went to this Chalcolithic age in South Asia, which basically now say constitutes Pakistan, India, Bangladesh, and Sri Lanka, and there was settlements, but there was no real kind of progress in human civilization. People were living in scatter. As you can see from this Chalcolithic age map, from 7,000 BC to 3,000 BC, there are all those scattered, human settlements. But, there was not the full-fledged, collective civilization. And so after this 7,000 years of Chalcolithic age, we had this Indus Valley civilization, which lasted maybe maximum 1,000 years. Okay? And this civilization was not a kind of rural or agriculture oriented. It was a city culture. They had a swimming pool, not the swimming pool, kind of, for public. They have a, structure to store grain, roads, and at one point, at the height of this civilization, at the city of Mohenjo-daro, an estimated 30,000 people are living. 30,000, just imagine, say 30,000 in 2000 BC will be more than, say, 300 billion people, if they have chance to live, in a normal fashion. But after 1,000 years, the civilization has, almost completely gone or moved towards, the south part. Okay, so what made these people to, move to a much more closer range from their scattered living? Again, that is the clustering. When people gather together in a clustering, there is interaction. There is an exchange of ideas. And maybe you can think about, like, again, I came with this room, why you are here, you could have stayed home and done everything online. But you are here, again, to form a cluster. And these clusters gives people to chance to talk, exchange ideas, or even fight, or even argue. But there's some progress. So that's what I said, civilization, or even the progress, in spatial econometrics, it comes from clustering. To continue clustering, those of us engaged in academic, I can tell you that our jobs are very secure, because research and training can never be fully outsourced to China or India. From time immemorial, this teaching had been always imparted from the home of the guru, the teacher. And those little training places at the home of the teacher basically now transform into schools, universities. A good university is nothing but, it's too simple to say, but I think is essentially a good cluster of good students and good teachers. Okay? So in that sense, cluster, plays a big role. But again, we have to be careful. All clusters are not good. There are some bad clusters, and that's what I say. In my title of this talk, that the civilization will end with clustering, unless something is done. I'm always optimistic. And what sense cluster could be bad? Think about these examples: pollution, traffic jams, global warming, deforestation, concentration of wealth. What I mean, the income inequality. Okay? And these are the kind of, I say, bad cluster. Okay? Or if you think of just the case of, for the time, the pollution. And in India, New Delhi has one of the highest polluted cities in the world. But if you think about India as a whole, 90% of it is hardly there is any pollution. I come from a village. I know there is no industry. There is hardly any motor vehicle. So no pollution. But the pollution becomes kind of a big headache when it concentrates or clusters around certain locations. Okay, so if you could somehow distribute the pollution of Delhi into some neighboring states like UP and Haryana, then it should be fine. That's not the solution really. Okay, or if you look at another case, particularly in United States, the high crime rates, particularly we talk about this called crime rate in Chicago. And again, I think, part of this can be explained by clustering and what I call segregation. Segregation is nothing but one form of clustering. Okay? And Chicago is a rich city, but there is a lot of crime. But I've seen in many poor countries, including India, other places, crime rates are much lower. Okay? Not because there is no segregation, but there is not this economic segregation in some sense. I have seen very luxury apartments and the coexistence of poor slum areas next to those apartments. And again, it was an economic choice because many of those, cleaners, washers, maids, those who work in the apartments, they live next to it, for easy transportation. Of course, in United States, there is another problem, the gun, but I'm not going to get into this. Okay? And so these are the kind of what we can call, the bad clustering. Okay? And now let me again go back to this spatial analysis, space. Okay, this space is very important. Let me emphasize this, or somehow tell this in a very crazy way. As you notice, I will tell a lot of crazy things because you will remember these crazy things. Okay. Now consider, say, yourself or myself. Here is a simple proposition, or a profound proposition, that I am alive if and only if I occupy a space. Okay? And again, this is not I'm saying. This is in fact, I just borrowed it from a poem I read, many years back in my language, Bengali. So let me tell you this poem, just part of it. Okay? প্রাণ আছে, এখনো প্রাণ আছে, প্রাণ থাকলে স্থান আছে, মান আছে, সমস্ত বাধা নিষেধের বাইরে আছে অস্তিত্বের অধিকার. Okay. And basically what it says, once you have a space, then you have life. And more things follow from there. Dignity, rights, all those things, follows from this. Once you occupy a space. Okay. And Okay, one thing I should emphasize here, that my talk is mostly directed to students and young researchers. Okay, those who are looking for kind of nice research problems or ideas. And then I would say to them that while we are in space, think about its twin brother. Who is the twin brother of space? Time. Okay? And as we know, time series analysis is a very mature field. Okay? And a simple way of thinking about problems is the following, that whatever has been done in time series can be attempted in spatial analysis. But of course, that's not very trivial. No? Time has this, what should I say, advantage. It has past, it has present, and there will be future. And now remember keywords of spatial analysis, the dependence, spatial dependence. And in time, you have time dependence, but there is only the dependence in time goes only in one direction. Okay? And so, but as you can see in space, we cannot say that. The dependence is much more complicated. That in fact, it makes it more interesting or more challenging. That's why it gives you kind of research problem to deal with many concepts that we have seen in the time series analysis. But there is an advantage in space. In time, you really cannot see time. Time is an abstract concept. Okay? But in certain way, when you talk about spatial analysis, we have this very concrete idea of the location. You see the location, you are sitting there. So your space right now on the chair that you are sitting. Okay? So I think that's very kind of, in some sense, an advantage of spatial analysis. Okay? So then you can talk about dependence since you see it, how things are dependent, how two people are connected. When you talk about network analysis, or you can talk about, say, Facebook. Facebook is a space. It was not there, a few years back. And in fact, we are creating lots of spaces. Okay, like Twitter, Facebook, and many years back, there is something called MySpace. Okay? And now you can see these, agents, or you can see these locations, and you can kind of, get some ideas, concrete ideas about how different locations or how different agents are connected with each other. Okay? And that can be exploited when we do the spatial analysis. And so, think about time series, what are people have done. There are some simple models, ER model, autoreducing model, moving average model, ARMA model. But then, last 30 years, the time series has really progressed much when it comes to the non-stationary time series. And in space, we have similar concept, anisotropy, which is not, stationary in spatial sense. And then other problems comes naturally, like unit root problem, co-integration problem, structural break. So we can also talk about spatial structural break. Okay? And 20 years back, a long time back, I used to work on ARCH models, autoregressive conditional heterogeneity. Then 20 years back, I was thinking about why not thinking about, search, searching for search, spatial ARCH models. And 2005, I presented a paper in Econometric Society World Congress, basically kind of proposing the search model and finding a lot of empirical evidence. It was more like an empirical paper. What happens in space, that the ideas will be similar, but theory could be very, very complicated, as I said, because of this, spatial dimension. The the complex dependent structure. Okay, I'm still working on the search model, no, because it's not a trivial thing to do. Okay, and again, what happens when as soon as you move from ARMA model to search model, we know what is happening. We are moving from linear dependence to non-linear dependence. So we now can also talk about non-linear dependence within the spatial structure. Okay, and so, but again, some could be borrowed from the time literature. Again, this is due to the common theme between time and space. The common theme is the dependence. And then another idea of research could be just look around. We are dealing with, say, econometrics, spatial econometrics, and there is a parallel thing going on called spatial statistics. The spatial econometrics and spatial statistics, I call them twin brothers. Twin brother, but they got separated from birth, and they are growing up, very differently. There's lots of very popular Bollywood movies that these two brothers, they get separated in the birth, and then they growing up in a different circumstances, and one becomes a hero and other becomes a villain. But here I don't know who is villain and who is spatial econometrics is the villain or the statistics villain. I don't know, but I think we need to bring this two people together, just like in the movies. Then these two brothers, they recognize, and then they may be running after the same girl, but then all problems are solved. Okay, all those tragedy becomes a very beautiful comedy. I think that's what we want to do. Try to bring lot of statistical tools to the econometrics literature. And if you look at time series literature, in the last 30 years, most of the contribution of in time series analysis came from econometricians. All those concepts I just talked about, unit root, co-integration, structural break. This is basically the contribution of econometricians. Okay? So I think by combining these two strands of literature, spatial statistics, spatial econometrics, I think there is a big mileage in there. Okay? And in terms of my own research, I'm working on, as I said, in the spatial arts or nonlinear dependence. But my more research would be like, producing not, of course, the models and also some tools. Remember we talked about tools? We have classified the civilization in terms of the tools they are using. That's why there is Stone Age, Copper Age, Iron Age, and so on. Okay? And then, and what are our tools? Okay? Again, the tools could be very bad. Sometimes you can do a lot of damage with tools. Okay, but no, we are going to do tools now. We have made tools only for good, peaceful purpose. Okay, there is a very famous statistician, Prashant Chandra Mahalnavis, in India, who is the founder of ISI, Indian Statistical Institute. In fact, he proclaimed that the statistics was the key technology of the 20th century. Okay, so now let me kind of give a bit rosy picture. Maybe we can make spatial econometrics as the technology of 21st century. Okay, in terms of this big data, machine learning, because when you talk about spatial data, it could be enormous. Okay, and so in that sense, this is nothing but a technology. Okay, and okay, so we have these tools. Okay, and statisticians and econometricians have tools like the simple way to classify them is like estimation tools and testing tools. Okay, just like you see in the slide. But what do we do with these tools? We build models. Okay, and you know what is models. No, you have seen lots of models, I know. Okay, but these models could be very elaborate. No, they can be dressed very nicely, or it can be bare minimum. Okay, like as you see in this slide. Okay, no wonder econometricians always fall in love with their models. Okay, but what I would like to say, the models differ depending on the purpose. Okay, and why you are using building this model for understanding the economy, or to predict the economy, or to kind of advise some government officials. So your model should be constructed based on a purpose in mind. Okay, and in my opinion, okay, it's okay to fall in love with your model, that's fine, but what I do, I subject my model with a rigorous testing and diagnostic checks. Just like if you see what is a good model, is not just discipline nicely, you have to walk in the ramp in your high heels, and just like a peacock in a natural way. Okay, so what I advocate, that a model should be tested thoroughly. Okay, and again, that it should be tested not just kind of like a one or two times. Okay, because what happened, I can tell you, no matter how much effort you put in building a model, all the models are wrong, but some are useful, and we are after these useful models. Okay, and when I say some models are wrong, in our econometric terminology we call misspecified models. Okay, so the idea would be how do you choose a useful model out of these many misspecified models. Okay, so the idea is to arrive to this useful model after subjecting many available models with a battery of tests. No, I was about to say a battalion of tests. No, battalion of tests is too much. You not just need a few tests. Okay, when trying to check or diagnostic checks your model. Just like when you go to a doctor, the doctor does a lot of things. They take your temperature, take your blood pressure, or maybe ask you to do also doing some blood tests and so on, or CT scan or endoscopy. In fact, I have just gone through those very recently, so I know how many tests you can go through. But again, this is just to diagnosis. Okay, what's wrong? Okay, and I call this, we know in testing, we know type 1 error, type 2 error, but I have this term, I call it a type 3 error. What is type 3 error? That means you are doing all these tests with a wrong model. Your test may be all right, a textbook test, Neyman Pearson lemma. But if you do Neyman Pearson lemma, use Neyman Pearson lemma, that is the kind of, it gives you uniformly most powerful test, but it is a wrong model, no, there is some problem. So we have to kind of allow this, the models can be wrong. Or some beautiful models working in the RAM, they might have some defect. It can be corrected. Okay, so that's what I talk about. This model testing or testing with misspecified models. I am an expert in testing. I think I can claim that because I learned testing from my mother. And anything you learn from your mother, it stays with you whole life. So I think I have to be kind of keep on doing testing. And my mother, who never went to school, and what I have seen her from childhood, cooking the rice, and then she will take a spoonful of rice from the vessel and place with her fingers to see whether cooked or not. And if I were present, I would insist on really putting them in my mouth and really testing. And so that is I have been used to from my childhood. Okay, And so you can see here, my mother in her kitchen, and then here she is sampling the rice and checking whether it is cooked or not. Okay. And one thing noticeable here, you see, she absolutely have no gadgets, no electricity, and very few amenities she needed, to do all these things. Okay. And so let us kind of put this into a little bit of mathematics, that you can check whether rice is cooked or not by so many ways, by in a finger, or you can just check by eating it, or sometimes what my mother will do, she will not even check anything. She will just put the right amount of the water, and as soon as the water is gone, she thinks it is cooked. So that's the easiest way, without absolutely no effort. Okay. And so let us put some mathematics in it. I call it Stat 101. Okay. The basic problem is testing say mean is 0 or not under a normal framework. Normal with mean mu, variance 1. This is the simplest model we can think about. And then you can apply Neyman-Pearson lemma and get the most powerful test. And again, it will be based on the sample mean. And if you do the likelihood ratio test by estimating the mean both under the null and under the alternative, again it based on the likelihood ratio test will be based on the sample mean. Essentially, it will be n y bar square, which is a pi square 1 distribution. Now, I already talked about that one of the tools of testing is a Rao score test, and which is exactly same as what we know in econometrics, the LM test. Okay, so you look at the score. Score is the derivative of the log likelihood with respect to the parameter. Then you evaluate it under the null. That's essentially the score function under the null. And if you look at the score function, in this case, it is exactly n y bar. Same that we have seen used in Neyman-Pearson lemma or likelihood ratio test. Okay? And so this Rao score test, as we see, there is no estimation involved. You get the score function and you evaluate it under the null. Okay? And you can see it geometrically. Geometrically, as you see in this little geometry here, that the likelihood ratio test is nothing but this, twice the area of this triangle here. Okay? Because we can write, that way. And Rao score test exactly the same area. So they are identical, at least this context. And in other contexts, they will not be identical, but they will be close to each other. But although they are kind of obtained in a different way. So in this case, under the null, mu is equal to 0. So there is, for Rao score test, there is absolutely no estimation involved. But of course, like ratio test, we need to estimate, under the alternative, that means when mu not 0. Okay. So there are kind of these three tests that we are very familiar with, in statistics. Okay. And in these three tests, as we see, Rao score test is like, you estimate the model under the null. That means under the restriction, mu is equal to 0. So under the restriction. And in the wall test, you do under the unrestricted model. Okay. So, and you can see that they almost look like fundamentally so different. Let us look at this difference in a very practical way. Suppose you want to check whether the dog that you have is have enough education or no. One way to check this, just let the dog go around and see how the dog behaves. If it behaves nicely when going around, fine. Otherwise, if you go and attack somebody, no. That's not a good way of testing, but that's one way, that's a world way. But I'm not teaching the world, right? Okay. And so you look at this picture here, when the dog is unrestricted, and we are looking at his behavior. Okay. Of course, when this kind of thing happens, you just reject the null. But in some time, I can just put the dog under the leash and see how it is behaving. And I call it, this is a more peaceful way of doing this. So look at this, this cute dog, and of course, he passes the test. Okay, he has enough, what you call disciplined education. Okay, but this is just for illustration, of course. Okay, so we'll be kind of using this idea of testing without estimating the model, or estimate the model under the null hypothesis. And most of the time, the null hypothesis will be certain parameters are 0. That means you don't have to do any estimation for those parameters. Now let us go back to our the fundamental model that we use, linear regression model. Okay, and as I said, each model is some way misspecified. Okay, and what way this particular model could be misspecified, linear regression model, or you can say what a misspecified model. That's not an easy question. So whenever we have a difficult question, I always go back to one of the gurus. Now you can see what is a misspecified model, and we can very well understand what is a correct model or a specified model. But a model could be misspecified in so many ways, so very hard to kind of pinpoint exactly what is a misspecified model. Okay, so now let me kind of illustrate whatever I said about this Rao-Score test in the context of a very practical example. It is more like using an example, and the data comes from Luke and Slane's classic book, the first modern textbook on spatial econometrics. Okay, so there is a beautiful data set called Crime in Columbus. So the Columbus city had like say 49 little locations, we call census tract, and he had data about the number of crimes, different kind of crimes, total number of crimes, and also data on income, median income, and median house prices in those locations. Okay, but I must add, this is just like an illustration. Okay, and we can estimate different kinds of model. First, the standard regression model. That's what I put out before. Y is equal to x beta plus u. Okay, and we can just do the OLS estimation. Now you see the OLS estimation. It has this is a very familiar example, so I won't go in detail. You see the OLS estimation, very nice. But then we can introduce spatial dependence. Again, it can be done so many ways. So let us look at two ways: spatial autoregressive or spatial error model. Okay. Now, once you add these, these two kind of, generalization to the OLS model, results is much improved. But then what happens? There is a problem. You can see the ACR model, ACE model are almost equally good. Even the parameters, ACR dependence parameter, it comes out to 0.42, and ACM, the error part dependence, come out to 0.56. Both are highly significant. In fact, ACM model is more significant. Now, these two dependents, we don't know whether one of them is present or both could be present. But how do you do this? Of course, I can test for rho is equal to 0 or lambda is equal to 0 separately. And then we can make a decision. Or we can test jointly. Again, jointly is automatically rejected. Okay? Or we can just do the standard Rao-Score tests. Okay? But this standard Rao-Score test, what I denote is called RS rho and RS lambda, there is a little problem. Because when I say RS rho, it is developed assuming lambda is equal to 0. Similarly, RS lambda is constructed under the assumption that rho is equal to 0. So in that sense, they're kind of testing with misspecified model. So we need the adjustment. Okay? And RS rho lambda, the joint part is okay because it is based on the whole model. Now all we need to do, that kind of adjust this RS row and RS lambda, and this adjusted version I call it RS row star, RS lambda star. And those could be obtained from RS row lambda, RS row and RS lambda. On all of them are based on OLS estimation. Now look at RS row star and RS lambda star in the table, in the slide. You see both RS row and RS lambda was highly significant, but only the adjusted version, that is RS row star, is significant and RS lambda star is not significant. That means the only thing we need to take care of is the SAR part. And as you can see, what is this construction is? The construction is kind of orthogonalization. Okay, that means from the array, from the score of row, that is D row, you get rid of the lambda part. Exactly same way, you construct D lambda star by removing the influence of the parameter row from the score of lambda. And then these two components, these two versions, D row star and D lambda stars, they become kind of mutually orthogonal. That means they can be viewed separately. Whereas the unadjusted score, the D row and D lambda, they are kind of influenced by each other. Okay, so this is what we sometimes call the robustification. Okay? And for this you can see or somebody could have estimated all the models, OLS, SAR, ACM and SSE, just like you see in this table. And there you can see from the SSE what I call the combined model. And this combined model, you can immediately see that rho is significant, but lambda is not significant. But you need the estimation part. Okay? But again, the estimating this big model, I mean relatively big, SAR and ACM, this combined model, in fact, it was not so easy even 10 years back. Okay? Because this combined model has some kind of identification issues. Okay? But what we need for this procedure of adjusted testing procedure or testing under misspecification, we just only need the OLS estimation. From the OLS, we calculate RS row lambda, RS row, RS lambda, these three unadjusted tests, and from there we can automatically calculate the two adjusted tests, RS row star and RS lambda star, and then check them. In this case, RS row star is highly significant, whereas RS lambda star become completely insignificant. That means we can just now jump from OLS to the, and in this context, the SAR model. Okay, so it almost looks like a free lunch. Okay, but we'll talk a little bit about, if I get a chance, there is a cost to pay. Okay, but this is the simplest procedure then we can think about. Okay, now here this is the simplest model we are talking about. No? Now when you go to spatial model, there is kind of huge a plethora of models depending on the data. Okay, so that's why I little bit talk about that in next. So the data that we just talked about, these are crime in Columbus data, and it was like a purely cross-section data. We have observation at a particular time on the 49 census tract. And so then we consider only simple models like SAR or ACM or its combination we call SSE model, which had AR component, autoregressive component, both in the regression as well as in the error term. Okay, so this is the kind of the simple spatial model. But depending on the data, we can get a wide range of spatial models. Now suppose we add the time component, then we have the panel data. Now we can talk about spatial panel data. Again, when you are in the panel context, many things can happen. You can have this, the error component part, it could be fixed or it could be random. Now as you can look at this table, the list of models that we have, in a panel, it could be static panel or also could be dynamic panel. Now, all our models may not be, in terms of location, geographic location. As we said, there's a wide range of, we can have spatial dependence, like in the Facebook. Okay, or you can think about the social interaction model, how individuals interact with each other, or how the high school kids, they interact with their peers. There is a big, issue of looking at the peer effect. Okay, and also you might have noticed when you have a simple SAR or SA model, there we have to specify the weight matrix. Okay, and it just comes there, and generally we assume the weight matrix are exogenous, and that makes life simple, but that is an assumption. Now we can also think about the spatial models with endogenous weight matrix. Okay, and again that opens up a completely another area of research and modeling. Okay, now we don't know which one of these effects are present, whether it is fixed effect, random effect, whether it is static, whether it is dynamic, or what kind of peer effect we are looking at, or whether the weight matrix is exogenous or endogenous, and all can be put into a testing framework. So in our simple cross-section context, crime data, we had just two parameters. We talked about rho, lambda. Now for each of these effects, we can talk about, one parameter to take care of one effect. We can have not just rho and lambda, we could have rho, lambda, delta, mu, sigma, gamma, tau, zeta, eta, so many things. And think about a model with, say, other than regression model y is equal to x beta plus u, then we have 8 more parameters for the complex model. Okay, and if you have to estimate all those 8 parameters, I think it is impossible. And also you don't want to do that, because estimation, you might get some result, it will be very unstable. So best thing to do, that use the principle that we already talked about, Rao-Score principle, which requires estimation only under the norm. So you don't have to estimate explicitly all these, rho, lambda, delta, mu, sigma, gamma, tau, zeta, eta, and all those things. Okay, and that's so now let us extend this approach of Rao-Score test into a much more complex model. Okay, so we can start at the very general model, incorporating as many things as needed and that we think, practically meaningful. Okay, and then we can test, presence of all those, parameters. Okay, but you might think, it's a trivial thing. Once you do for one model, then you can do for all other models. But specification search, in the spatial context particularly, is not that easy, because once we want to develop the specification search for this model, what we need to do, as you can see in this list that I am giving you now, that we have to consider model my model. There is no kind of one formula. As soon as you change the model, everything changes, and the algebra is very complex. And also, for each model, the regularity conditions will be different, depending on the structure of the model. Like very simple, maybe we talked about W. A lot of things depend on the weight matrix. And again, it's a really problem if you are thinking about fixed W or endogenous W. You need different regularity conditions. Okay? And after you solve these things, you do the huge algebra. But one good thing about Rao-Score test, at the end of the day, you get some beautiful algebraic formulas. Okay, not like as good as E is equal to mc square, but some nice formulas. You can see it, and you can never do that with the form of like wall test or like ratio tests. There is no kind of closed form expression of those test statistics. But here, Rao-Score test, there is a closed form expressions. Okay, so you have a complex model, but because of the Rao-Score test principle of testing, that you need only the estimation of the null, that means you can just do OLS. That's all you need. Run the OLS and get the test statistics. But of course, these tests that you're talking about a large sample test. So what you need the next step, investigate the final sample properties of these tests in terms of size and power. Okay? Okay? So this takes care of the theory. But then how good is theory? You need to kind of illustrate with some substantive applications with the real data. What do we gain by applying this test to this real data? Okay? And then last step could be, the programming could be complex. Although the closed form expressions, still, algebra could be, but you might want to have this, make the whole test procedure available as, user-friendly software. Okay, so these are the kind of steps you need to do for each model that you want to test. Okay, so it is a kind of model by model. You need to do all those things, and you can see this is not a one-man job. It requires a lot of manpower. Okay, so but I am very lucky. I am blessed with two young researchers. As I say, manpower. So I have Dr. Usman Dogan and Dr. Suleiman Taspina. Okay, and we just started working basically last year. Usman spent a semester at UIUC, and Suleiman visited UIUC for a couple of times. And so, as you can see, this young man, very active, and so we are able to do or tackle some of these problems. Okay, with these three people together. Okay, and so of course it will be impossible for me to kind of summarize what we have done and what we planning to do. Okay, so let me just give you very quickly the list of the joint papers that we have recently finished, and we are working another half a dozen paper right now, and so but then what we have really achieved, that within a short time we are able to kind of take model by model and then develop specification test, which again being put into software so that it will be readily available for applied researchers to use. How it is possible to do this? Because we have formed a very fruitful cluster of 3 authors. Okay, again the keyword is a cluster. You can achieve a lot of mileage having this few people together. Okay, so I would say my young scholar friends, if you want to be more productive or solve a lot of problems, okay, one way would be form a cluster of some productive researchers. Okay, so again the cluster. I'll come back to cluster again, but so this will be basically the quick summary that I've been doing in the context of specification search for different spatial models. Talking about cluster, it seems clusters bring, say, economic agents or the geographic locations together. However, sometimes individuals can repulse each other, and that's a dependence. Yes, it's a dependence, but a negative one. A good real-life evidence of this you can see in the airport waiting lounge. I mean, there, when you get there, you rarely take up a seat next to a person, next to a seated person, if there is, you have any other choice. Just look at the following, real pictures taken in the airport lounge. And you notice the empty space between these occupied seats. For this kind of negative dependence data, if you just estimate an ACR model, it will be negative. Okay, and let us recall the time series case. I have not seen a single substantial empirical paper with time series data that gave negative estimation of autocorrelation. If you can find any, just let me know. I'll give you some instant cash prizes. Okay, So this negative correlation is rarely observed empirically in time series data. But when it comes to spatial data analysis, the prevalence of negative dependence is not at all uncommon. With my former student Sina Kao, I wrote this paper, as you see in this title here, with a curious title, The Curious Case of Negative Spatial Dependence. Okay, and there we cite many applied papers with negative both rho and lambda in the context of SAR and SAM model. And you can see now also in this list. Okay, and here look at this example of this list, that here the clustering occurs with a more like in a competitive setup, and the other examples that you talked about clustering, and there you get dependence more through the cooperation. Okay, and when this competition also outweighs the cooperation, you also might end up at the negative estimate of the autocorrelation, spatial autocorrelation. Okay, and in this table you see this when we have negative autocorrelation in the context of, say, local tax competition or local government competition to obtain federal funds. Okay, and this negative autocorrelation is not just kind of a trivial thing. Whenever we do spatial analysis, one of the idea is to do the impact analysis, looking at the impact effect of, say, certain policies on the outcome. Okay, and this the impact formula, it could be direct or indirect. It depends of course on this the weight matrix that we use, or like the whether exogenous weight matrix or endogenous weight matrix, but also on this estimation of these parameters rho and lambda. Okay, so your formula will be, or even the end result will be completely different whenever you have this negative values of these autocorrelation parameters. Let me also mention another thing about cluster, positive, negative, or good or bad. In fact, there is a lot of bad clusters. Example of like these cluster bombs. Okay, but no, we are not going to get into that. What happened long before the spatial statistics or econometrician in doing spatial analysis, there had been a lot of work had been going on something called cluster analysis. Okay, because the data sometimes come in cluster. Okay, they are all like a bunching. And if we look at the current work on cluster analysis by econometricians, what I am observing, they're mostly concentrating on the inference. And sometimes what I call them, whitewashing the cluster structure. What they are mostly engaged in, finding valid standard error so that we can have valid t-tests. Okay, in the presence of cluster data. But what I think would be more useful, to find the causes of this cluster or this formation of this cluster through spatial analysis. It is not just the kind of like treating just the symptom, but maybe to find out the cause of the symptoms also would be useful. I think this will be a very fruitful research area for my young scholar, that to kind of merge this cluster analysis literature with this that we have been talking so far, the spatial analysis. Okay, so that would be, I think, a fruitful way of doing research. After some serious topic of testing models, negative dependence, let me now touch on a light-hearted topic. As you can see, I'm very relaxed, no tie, and so I also want to be relaxed right now. I think many of you, go to the church for mass on Sunday. But have you ever thought about, is there any connection between the church and the massage parlor? No, I'm not really no way trying to be disrespectful to anybody's faith or belief. But what is the mass? That many of us go on Sunday. Mass is a gathering, putting things together. See, you cannot have a mass just with one churchgoer and the minister. No, then it won't be a mass. No, and very well your minister could have come to your house and do the service. No, that's not a mass. So mass is gathering. Or think about our keyword, clustering. People coming together. We talked about civilization. Now let us talk about the basic component of living, the bread. Okay, you know how the bread is made? First we make a dough. Okay, and how the dough is made. Okay, I don't know whether you have seen, how the dough is made. Basically, what you do, you massage. You massage the floor with water. Okay, and then after massaging, you transform that water and flour into a mass. After the mass is done, of course, then there are two more steps, as you see in these pictures. Okay, and that basically complete, the bread making process, and that's the kind of just like rice, bread is the lifeblood of human being. And what about this massage parlor? That possibly provide comfort to people, maybe for both mind and body. And what is the tool they use in massage parlor? Same, just like making the bread. You do this. That is massaging, and you are smoothing things. In fact, the fundamental idea of many of the statistical procedure is massaging. Okay? Think about the basic data analysis tool. Again, we're talking about the tool. That's the histogram or the bar diagram. And one of the most advanced techniques in statistics is smoothing. Smoothing of many kinds. Okay? Now going back to the histogram, basically what we do there, we smooth the histogram to get, say, kernel density. That's why I won't call it smoothing. I will call it, massaging. Okay? If you look at the slide, what we do there when you are kind of starting from a histogram. With the histogram, what we do? We massage all those, bars. If some bar is too long, you push it down. If some bar is too low, once you push this one, other goes up. And then we obtain a good looking graph. Okay? Because remember what you talked about the model? A model must be a good figure. And histogram figures are very bad, It's not a good looking figure for histogram. So what we do? We massage it, then get a smooth curve. Because we like smooth figures, like a good model. Okay? And so that's what, Again, I'm mentioning this because I feel it is connected with the whole concept of cluster, putting things together. Massaging in some sense also, putting things together in some sense. Okay? And okay, I just realized that, I have taken a lot more time than intended. Okay? So my job is done, and one good thing right now, you have no opportunity to ask me any question directly. But however, no, I would really love to hear from you. If you have any comments or questions, suggestions, please send them to me at this particular my email address, and also I'm in the Facebook. Okay, so feel free to write to me whenever you can. Okay, so now the movie comes almost to the end, and it is to time to acknowledge the people involved in it. People involved behind the curtain. Remember, in the movies, 2-hour movies, there will be 10 minutes of those titles of acknowledgement. No, but I have only one person who performed the most difficult task in producing this video, and he's Professor Umut Uyar, and he's at the Pamukkale University, Denizli in Turkey, and he's currently a visiting scholar at UIUC this year, and he definitely deserves all the applause. So let us all give a big clapping hand to Dr. Umut Uyar. Okay, so thank you very much.